Hello students, yesterday we have seen how to get H's from Es, and we came to know that both electric field and magnetic field are everywhere normal to the direction of the propagation of the wave. It means the field lies in a plane that is orthogonal to the direction of the wave propagation. So in this way they form an electromagnetic wave that has no electric or magnetic field components along the direction of the propagation, and that is the wave which is called transverse electromagnetic wave. And from the electric field component of the wave we find this is the amplitude which is varying sinusoidally. So the electric field component amplitude is E naught e to the power minus alpha z. So from here we can say amplitude of the wave is E naught e to the power minus alpha z. Let us analyze this. And if alpha is equal to 0, what it means? If alpha will be 0, then this term will be 0 and this term will be 1. The amplitude of the E should be equal to the E naught. So E will be equal to the E naught, that is constant irrespective of the wave propagation. And if alpha is different from 0, then this value decreases with the increment of z. So the value of E decreases exponentially with z. And if we plot this, then we can find at z is equal to 0, this becomes equal to 1 and it becomes E naught. And as z increases, then it decreases exponentially like that. This is amplitude is decreasing with z. Okay, and this is E naught, and this function is E naught e to the power minus alpha z. We can find from here, as the wave propagates in the direction of z, it decreases or attenuates in its amplitude. Okay, and the factor of decrement is e to the power minus alpha z. That is why alpha is known as the attenuation constant or attenuation factor of the medium. Okay, and alpha is, the unit of alpha is Npr per meter. Np is nothing but Npr. Okay, Npr per meter, and it is also represented in decibel. That is 1 Npr is equal to the 20 log E base to the 10 decibel in decibel. So if we will solve this, then it will be 8.686 decibel. So the unit of alpha is Npr per meter or decibel. Now after attenuation constant, let us talk about the beta, that is phase constant. So this part is phase part, that is omega t minus beta z. and beta here, it is the measure of phase shift per meter, or we can say phase shift per length, and is called phase constant. Okay, so beta is phase constant, and that is phase shift per length. It is also named as wave number. Okay, and its unit is radian. This is radian per meter. So per meter will be cancelled out. So the unit of beta will be radian per meter. Radian per meter. We have propagation constant, that is gamma. We know that this is alpha plus j beta, and if we recall, then we find out that it is j omega, I think mu sigma plus j omega epsilon. Yes, this was the gamma. And if we try to solve the under root, then we find the real and imaginary part, that we can get alpha will be real part of this, and imaginary part will be beta. So alpha we will get omega. I'm not going to solve, just I'm writing final result, that is omega, and even though you need not to solve it, mu epsilon by 2 under root 1 plus sigma divided by omega epsilon square minus 1. This is alpha, and in case of beta, just we have to replace it with plus sign, that is mu epsilon divided by 2 1 plus sigma divided by omega epsilon square plus 1. Okay, so we have alpha and beta from here. Now it is required to simplify this, and for simplifying this factor, the new term is defined, that is loss tangent. That is important one, loss tangent. And loss tangent is defined as the ratio of the conduction current density, that is Js, to the displacement current density, that is JDS, in a lossy medium. Okay, and this ratio is termed as loss tangent. Okay, and we know Jc is equal to sigma E, okay, conduction current density, and in case of phasor form, we can write Jc is sigma Es. Okay, we have discussed this, there is no need to discuss again. And similarly, the Jd can be epsilon, if we can remember, del E over del T, and from here in phasor form, time varying domain, we can write epsilon del over del T, it can be J omega, and E can be Es. Okay, so we have JDS and JCS. Okay, or we can say JS simply. So to find the loss tangent, just we have to take the ratio of this to this. So for loss tangent, we will do JCS divided by JDS. That will be sigma ES divided by J omega epsilon ES. Okay, and in magnitude wise we can get epsilon can be cancelled out. The remaining term will be sigma divided by omega epsilon. This is nothing, just loss tangent, and it is also indicated by tan theta. Okay, so this tan theta is named as loss tangent. So we can write tan theta is loss tangent and theta is loss angle. Loss angle. Now put this tan theta in alpha beta equation to simplify that. Then we can get alpha is equal to, put here, omega, this term will remain as it is, mu epsilon by 2. This term will be 1 plus tan square theta, that will be sec theta. So here we can write sec theta minus 1, and beta can be omega, remaining terms will be exactly same except the plus sign will be there. So it will be sec theta plus 1. Okay. Now if we divide alpha by beta, then we can find a simplified result, that is alpha by beta. That will be sec theta minus 1 divided by sec theta plus 1. From here we can say that if tan theta is higher, it means loss tangent is high, then sin by cos, sec theta will be high. Okay, and if sec theta is high, then we can say this term is higher, and higher the value of alpha will indicate the higher will be the attenuation of the medium. In this way we find that tan theta, or simply theta, may be used to determine the lossy nature of the medium. A medium is said to be a good, or we can say lossless perfect dielectric if tan theta is very small. Okay, so if tan theta is very small, then we can say sigma will be very lower than omega epsilon. Okay, and a good conductor will be if it is very large. So it is good dielectric or perfect, not perfect, good dielectrics or good conductor. It will be tan, good conductor, it will be very high, that will be sigma will be very greater than omega epsilon. So from here what we can obtain, that a good dielectric can be good conductor with the variation of frequency. Okay, so we can say one sentence regarding these two. A medium that is regarded as a good conductor at low frequency can be considered as good dielectric at very high frequency. Okay, when it will be higher than this, then it will be good dielectric, and until it is lower than this, it is good conductor. Hopefully it is clear. And in the beginning we have derived that this is the theta n, that is the lagging of h from E, that is due to the intrinsic impedance. So from this theta n and this theta we can find theta is equal to this attenuation constant, loss tangent. From here theta is equal to the 2 theta n. Okay, hope until this point the things are okay. Now plane wave we have discussed when it is traveling in the lossy medium. Lossy medium means the conductivity of the medium is not zero. Now we will consider the case when the wave is traveling in other than the lossy medium. Now let us consider the case of lossless dielectrics. In this case we will try to find all the parameters again, that is alpha, beta and intrinsic impedance and loss tangent. One by one we will try to find once again. So in this case we know the conductivity is 0 as it is lossless, and from here we will start our finding from the this help. So we will start gamma, we have that is j omega mu sigma plus j omega epsilon, and that can be further written as, keeping this 0 we can write j omega mu j omega epsilon, that is this, and further we can write j will be out, omega will be out, the inside parameter will be mu epsilon. So from here we find gamma is equal to alpha plus j beta, we know this, and that is equal to the j omega mu epsilon. Okay, now we can relate these two parts. Real part will be equal to the real part like this, and imaginary part will be equal to the imaginary part. So from here we can find alpha will be equal to the 0 and beta will be equal to the omega under root mu e. Okay, so if alpha is 0, just in the previous case we have discussed, if alpha is 0 then the amplitude is, it will be equal to the 1, and the amplitude is will be equal to the E naught, means it will be constant. So from here we can find in lossless dielectrics the attenuation will not take place and amplitude remains constant. Okay, now let us try to find beta. From the wave equation we have beta is equal to the frequency of the wave divided by its velocity. It is derived formula, and just we are not interested to derive it again, just we have this formula from somewhere, where u is the speed of the wave and omega is the frequency of the wave. Now from here we can say u will be omega by beta, and for lossless dielectrics the beta is given here. So from there we can write frequency divided by frequency mu epsilon, and after simplification we can find 1 by mu epsilon, that is the speed of the wave. So in case of lossless dielectrics the speed of the wave is 1 by mu epsilon. Okay, now the intrinsic impedance that we indicate by zeta. So this, the formula for this is j omega mu divided by sigma plus J omega epsilon. I think this is the formula, and we have derived it yesterday. In case of lossless dielectrics, it will be 0, and the remaining term, this and this will be cancelled out. The remaining term will be mu by epsilon. So this will be intrinsic impedance in case of lossless dielectric media.